Hey there, science enthusiasts! Today we're strapping on our safety goggles and diving into the fascinating world of chemical reactions. Get ready for a wild ride as we explore the amazing transformations that happen when different substances interact. Let's get started. Alright, science sleuths, let's kick things off with combination reactions. Picture this. You've got hydrogen and oxygen just hanging out. Then bam, they collide with enough energy and combine to form water. That, my friends, is a combination reaction in a nutshell. In a combination reaction, two or more reactants, which can be elements or compounds, get cozy and form a single product. Hydrogen gas, H2, is highly flammable, while oxygen gas, O2, is essential for breathing. When they react, they form water, H2O, a stable liquid that's essential for life. Another cool example, the formation of rust. When iron, Fe, hangs out with oxygen and water for too long, they form iron oxide, Fe2O3, which we know as rust. Combination reactions aren't just limited to chemistry labs, they're happening all around us, even inside our bodies. When our cells need energy, they combine glucose, from the food we eat, with oxygen to produce carbon dioxide, water, and energy. So, how can you spot a combination reaction in the wild? Look for clues like the formation of a single product from multiple reactants. And remember, energy is often released in these reactions, sometimes in the form of heat or light. Keep an eye out for them as we explore the wonders of chemistry. Hold on to your lab coats, everyone, because we're about to delve into the world of decomposition reactions. If combination reactions are like building a Lego tower, then decomposition reactions are like taking that tower apart, brick by brick. It's all about breaking down a single compound into two or more simpler substances. One classic example of a decomposition reaction is the electrolysis of water. Remember how we combined hydrogen and oxygen to form water? Well, we can also use electricity to split water molecules back into their elemental forms. Another example is the thermal decomposition of calcium carbonate, CaCO3, commonly known as limestone. When we heat limestone, it breaks down into calcium oxide, CaO, and carbon dioxide, CO2. This reaction is super important in the production of cement. Decomposition reactions are also essential for our survival. Our bodies use them to break down food molecules into smaller, more manageable units that our cells can absorb. So how can you tell if a reaction is a decomposition reaction? Look for clues like a single reactant breaking down into multiple products. Decomposition reactions might sound a bit destructive, but they play a vital role in the natural world and in many industrial processes. Get ready for some chemical drama, folks, because we're about to explore the fascinating world of displacement reactions. These reactions are all about competition, where one element tries to steal the partner of another element in a compound. It's like a chemical version of musical chairs. A more reactive element displaces a less reactive element from its compound, forming a new compound in the process. This is a fundamental concept in chemistry that showcases the dynamic nature of elements. One of the most famous examples of a displacement reaction involves zinc and copper sulfate. This classic experiment is often demonstrated in chemistry classes. When we dip a shiny piece of zinc metal into a blue copper sulfate solution, something amazing happens. The blue color starts to fade and a new substance begins to form. The zinc, being more reactive, displaces the copper, forming zinc sulfate and leaving behind a reddish-brown deposit of copper metal. This visual transformation is quite striking. Another example is the reaction between iron and copper sulfate. This reaction is equally fascinating and demonstrates the same principles. Iron, being more reactive than copper, displaces the copper from copper sulfate, forming iron sulfate and depositing copper metal. This process is used in various practical applications. Displacement reactions are used in various industrial applications. They are crucial in processes that involve extracting metals and purifying compounds. For instance, iron is used to extract copper from its ores in a process called smelting. This method has been used for centuries to obtain pure metals. And in the thermite reaction, highly reactive aluminum displaces iron from iron oxide, releasing a tremendous amount of heat and light. This reaction is so intense that it can even be used for welding. So how can you predict if a displacement reaction will occur? The answer lies in understanding the reactivity series. That's where the reactivity series comes in handy. This chart is an essential tool for chemists. This handy chart ranks elements based on their reactivity. It helps predict which elements can displace others in a compound. An element higher in the reactivity series will displace an element lower down from its compound. This principle is fundamental in predicting and understanding chemical reactions. Displacement reactions are a fascinating example of how elements compete for bonding partners. They reveal the dynamic and competitive nature of chemical interactions. Get ready for a chemical square dance, everyone, because we're diving into the fascinating world of double displacement reactions. These reactions are like a well-choreographed dance where ions from different compounds switch partners to create something entirely new. These reactions are all about swapping partners, where ions from two different compounds switch places to form two new compounds. It's a bit like a chemical version of musical chairs, but with a lot more precision and predictability. One of the classic examples of a double displacement reaction is the reaction between sodium sulfate and barium chloride. This reaction is often used in educational settings to demonstrate the principles of double displacement. When we mix these two clear solutions, something spectacular happens. The clear solutions suddenly turn cloudy, indicating that a new substance is forming right before our eyes. The barium ions from barium chloride react with the sulfate ions from sodium sulfate, forming a white precipitate of barium sulfate. This precipitate is a solid that settles out of the solution, making the reaction visually striking. Another fascinating example is the reaction between silver nitrate and sodium chloride. This reaction is not only interesting but also has practical applications in various fields. When we mix these two solutions, a white precipitate of silver chloride forms, while sodium nitrate remains in solution. This reaction is a classic example used in chemistry labs around the world. This reaction is often used to test for the presence of chloride ions in a solution. It's a simple yet effective way to identify chloride ions, making it a valuable tool in analytical chemistry. Double displacement reactions are used in various applications, including the production of fertilizers, pigments, and even medicines. These reactions are crucial in industrial processes that produce everyday products. For instance, the reaction between sulfuric acid and calcium phosphate is used to produce phosphoric acid, a key ingredient in fertilizers. This reaction helps in creating nutrients that are essential for plant growth. So, how can you tell if a reaction is a double displacement reaction? There are a few telltale signs to look out for. Look for clues like the formation of a precipitate, a gas, or water. These indicators can help you identify whether a double displacement reaction has occurred. Double displacement reactions are like the ultimate chemical mixers, bringing together different compounds and shuffling their ionic partners to create new and exciting combinations. They showcase the dynamic nature of chemical interactions. They're a fascinating example of how even the smallest changes in a chemical equation can lead to dramatic and visible results. These reactions highlight the beauty and complexity of chemistry. Keep an eye out for these reactions in your experiments. They are not only educational, but also a lot of fun to observe and analyze. Alright, electron enthusiasts, it's time to unravel the mysteries of oxidation and reduction reactions, often called redox reactions for short. These reactions are fundamental to understanding how different substances interact at the atomic level. These reactions are all about the transfer of electrons. Like a tiny game of chemical hot potato. Electrons are passed from one atom to another, causing changes in their chemical states. Imagine you have two friends, let's call them Oxy and Red. They love to play this game of electron give and take. Oxy loves to gain electrons while Red is all about giving them away. This dynamic duo helps us understand the core principles of redox reactions. In an oxidation reaction, a substance loses electrons just like Red. This loss of electrons can lead to significant changes in the substance's properties. In a reduction reaction, a substance gains electrons, just like Oxy. This gain of electrons can make the substance more stable or reactive depending on the context. And here's the catch: oxidation and reduction always go hand in hand like two sides of the same coin. You can't have one without the other. One of the most relatable examples of oxidation is rusting. It's a process we see in our daily lives, especially with iron objects. When iron is exposed to oxygen and water, it undergoes oxidation, losing electrons and forming iron oxide, which we know as rust. This process weakens the metal over time. Oxygen, being the electron-hungry element it is, gains those electrons, undergoing reduction in the process. This is why rust forms so readily in moist environments. Another example is the combustion of fuels. This is a redox reaction that powers engines and generates heat. When we burn a candle, the wax, a hydrocarbon, reacts with oxygen in the air. This reaction is a classic example of a redox process. The carbon in the wax loses electrons, oxidation, to form carbon dioxide, while oxygen gains electrons, reduction, to form water. This is why we see both carbon dioxide and water vapor as byproducts. This transfer of electrons releases energy in the form of heat and light, which is why we see a flame. The energy released is what keeps the candle burning. But redox reactions aren't just about rust and fire. They play a crucial role in many other chemical processes. They're essential for life itself. Without redox reactions, our cells wouldn't be able to function properly. Our cells use redox reactions to generate energy from the food we eat. This energy is vital for all cellular activities. During cellular respiration, glucose is oxidized, losing electrons, while oxygen is reduced, gaining electrons. This process releases the energy our cells need to survive. So how can you identify oxidation and reduction? It's all about tracking the movement of electrons. Keep an eye out for changes in oxidation numbers, which tell us how many electrons an atom has gained or lost. These numbers are key to understanding redox reactions. Redox reactions are like the hidden engine of the chemical world, driving countless processes from rust formation to energy production in living organisms. They are fundamental to both the mundane and the extraordinary aspects of chemistry. Congratulations, science explorers! You've successfully navigated the exciting world of chemical reactions. Remember, mastering chemical reactions is like having a secret code to unlock the mysteries of the universe. And hey, before you go, don't forget to test your knowledge with our quick revision and MCQs at the end of this video. Until next time, keep those brains bubbling.